Hello, in this video we're going to talk about Fubini's theorem. So Fubini's theorem says if f is a continuous function on R, which is the set of xy points, such that a is less than or equal to x is less than or equal to b, and c is less than or equal to y is less than or equal to d, then the double integral over R of f of xy dA is equal to the integral from a to b, integral c to d, f of xy dy dx, and that's also equal to the integral from c to d, integral a to b, f of xy dx dy. So what Fubini's theorem is really saying is that you can do your integral with respect to y first on the inside and then do your integral with respect to x, or it could be the other way around. Basically, you could do your integral with respect to x and then do your integral with respect to y. So what Fubini's theorem says is that roughly if f is continuous, then you can change the order in which you do the integration. You could do it with respect to y or with respect to x. You can change them back and forth and you'll get the same answer. Okay, that's what Fubini's theorem gives us. So that's a really good theorem to keep in mind, because sometimes we get an integral and one way might be really hard and one way might be really easy. So let's take a look at the example given by the double integral over R of y times sine of xy dA. And R is the rectangular region where x goes from 1 to 2 and y goes from 0 to pi. All right, now one way to do this is to say the integral from x equals 1 to 2, integral from y equals 0 to pi of y times sine xy dy dx. This is going to be difficult. It's not impossible, but this is going to involve integration by parts. So we can do that, but maybe there's an easier approach. So the other approach is to change the order of integration, and since our integrand is continuous, by Fubini's theorem we'll get the same answer no matter which way we go. And the second approach is a little bit easier here, so let's take a look at how that would work. We're integrating first with respect to x, so y is a constant and we can bring that out in front. Okay, so let's do a u substitution. I'm going to let u be equal to xy, and keep in mind we're integrating with respect to x. So I'll say with respect to x. So if I look at du dx, that just gives me y. In other words, du equals y dx. And look at how lovely that is. We've got a y dx sitting right there in our problem. All right, so that's going to work out lovely, and let's just tidy up a few other pieces. When x equals 1, that implies that u equals, well, let's plug that in. Up here, u equals x times y, so that means u is going to equal y. And also, when x equals 2, that implies that u is going to equal 2y. Right? So let's see what we have. And now this is a pretty lovely integral to integrate, so let's do that. When we do the antiderivative of sine, we get negative cosine. And evaluating our limits of integration, we have a minus and negative cosine y, so we'll make that a plus. And now we just have to integrate with respect to y, evaluating our upper and lower limits of integration. We get negative 1/2 sine of 2 pi plus sine of pi minus whatever we get when we plug in the 0. So we get negative 1/2 sine of 0 plus sine of 0, and we know sine of 0 is just 0, so these terms are just 0. And over here, sine of 2 pi, we know that that's 0, and sine of pi is 0, so the whole integral was, at the end of the day, evaluated to be just 0.